Hello everybody, I'm Teresa Liberto, and today I will show you a fresh approach on low CO2 binders. So I would like to start with a very short introduction. I'm from Italy. I did both my bachelor and master degree in chemical engineering at the University of Pisa. Then I moved to Lyon for my PhD in physics, in which I studied the physicochemistry of calcite colloidal suspensions, which are model system for cement, from macroscopic rheology to microscopic interaction. And then I moved to Vienna at TU Wien in the research unit of building materials as a postdoc. I got a tenure track position on sustainable cementitious materials, and since 2020 I'm an assistant professor in the same research unit. What I do is rheology of dense cementitious suspensions. So I put together a bit of chemistry, physics, material science, and civil engineering. I study cementitious pastes via SAOS, or small amplitude oscillatory shear, and also classic flow measurements. The motivation of my work is to reduce the CO2 emission of construction industry for a more sustainable future scenario, which will include locally sourced alternative cementitious materials with variable chemical composition. So we need to be ready to study the physicochemistry of these cementitious pastes and also interaction immediately after the contact with water via SAOS and complementary techniques. I hope I will convince at the end of this talk that this is important. And before going into more detail, I would like to show you what is SAOS in the first place. So SAOS, or small amplitude oscillatory shear, is a test that needs to be made with a rheometer, which I try to sketch here. The most important part is the head of the rheometer, where there is the motor, which can impose a certain torque. And it's important to make this measurement that we can have a very low minimum torque. For example, ours has 0.5 nanonewton meter. This because we want to impose a very small amplitude oscillatory deformation, and we want to measure an amplitude oscillatory stress. We can also do the contrary, the opposite. And we expect a phase angle between 0 and 90 degrees because we are testing a viscoelastic fluid. Here you can see the geometry that we normally use for SAOS is a plate-plate geometry with accelerated upper and lower plate to assure the grip and avoid wool slip in between plate and paste. So the complete response of material to a periodic deformation gamma can be expressed by the shear complex modulus G star as the ratio between a complex stress and deformation, or as a sum of a storage or elastic modulus and a loss or viscous modulus. So the storage modulus G prime describes the ability of the material to store and release energy upon deformation, while the loss modulus, or G double prime, represents the energy dissipation due to the internal friction linked to molecular motion. What we can do with SAOS? So the first test I do every time I have a new material is the amplitude sweep, which consists in imposing a range of amplitude oscillatory deformation from a very small value, as you can see here, 10 to the power minus 5, to probe the interaction at the nanometer scale at an imposed constant frequency, because cementitious materials are not dependent from the frequency we choose. And this test can last from 30 seconds to a couple of minutes, depending on our elastic modulus, and consist in trace the G prime and G double prime as a function of gamma, or amplitude oscillatory deformation. At low amplitude oscillatory deformation is where we have our linear viscoelastic regime, so where the G prime and the G double prime are linear or constant with gamma. This area, where SAOS happen, is characterized by a linear storage modulus and a critical strain, and is our area of interest. After that, we have not anymore a solid-like behavior, and we don't probe anymore our structure, microstructure at rest, but we start to enter in a liquid-like regime in which both moduli drops and the particles start to detach. If we focus on this linear viscoelastic regime and we impose a small amplitude deformation smaller than the critical one, so here, for example, at a fixed frequency, we can follow the structural buildup of the paste, or what we can call physicochemical evolution, and this link with what is happening inside our paste. With the time structuration, we can plot the storage modulus as a function of time, and here I show you two different samples. One is a raw clay, which is unreactive, so the storage modulus doesn't evolve with time. OPC instead, immediately after contact with water, starts to react, and the G prime increases with time. Faster is the reaction, higher is the reactivity, higher is the chemical evolution of the sample. So I would like to show you some questions and go through together. And they are the questions that I ask myself when I start to work with cement. So can SAUS decipher the buildup of cohesion in cementitious system and describe the physicochemistry of these pastes, and what we really want, help develop new sustainable materials? Let's start with the first one. To reply to this question, I will show you some project in which SAUS is coupled with the X-ray powder diffraction and surface force apparatus. Before that, I would like to share you this schematic in which I show you the origin of early cement cohesion. So here I sketch a C3S grain or a cement grain. I use C3S because tricalcium silicate is the main constituent of cement and can be used as a model system. And once we put our C3S grain in water, we have an immediate dissolution in several ions and a precipitation of calcium silicate hydrate. Nanometer scale, so nanodisk of CSH, start to form on the surface of C3S. And when the pH raised, because we have a lot of OH- in solution, this flat disk became negatively charged and create an overall attractive electrostatic force development between CSH surfaces and also C3S grain. Then, if we wait minutes, hours, we have a build-up of a CSH gel network because we have an house of cards. Now this go one up to the other. And then we call it, in fact, the CSH, the glue of cement, and then we go through hardening and setting. The time window that I study with rheology is from second to hours after mixing. And I picked this very nice figure from the modeling, in which you can see that the CSH go from a nano scale to a micro scale. I found it really nice to show you the complexity of CSH, and it evolves with time. So it will be really nice to also be capable of modeling what is happening at the very beginning. For me, now the dissolution precipitation. So if someone wants to make a collaboration, because there is a very huge modeling community here, I'm more than happy. For now, what I can show you is how I trace the early stage cohesion due to the CSH formation of a C3S paste and a CSH gel, in which a spoiler CSH is already formed. So in the C3S paste, we mix C3S powder, the pure one, and distilled water. The CSH gel instead is made in the lab, and it takes a couple of weeks to form and be completely reactive. We do a time structuration at impose small amplitude oscillatory deformation gamma that you have here and a constant frequency, and we use a Mossberg chamber surrounding the plate to avoid evaporation. If you see the storage modulus evolution as a function of time, You can see that the CSH has no evolution at all because everything is already formed. So there is no new reaction once we put it in the rheometer. And then the C3S that is charged immediately after mixing with water has an evolution that is probably due to the dissolution precipitation that I showed you before. But in order to be 100% sure that this is what we measure here, we do some SFA or surface force apparatus investigation. So this instrument is pretty rare. To my knowledge, there is one in Oslo, one in Vienna, in which we also have an interferometric technique, which can give us the changing distance between confining walls. So we can check how the contact area evolve, and in our case, the film thickness of what we are going to precipitate. You can see that we can measure, we deposit calcium silicate by laser deposition on mica substrate, and then we add water. And we follow the adhesive pressure and the film thickness as a function of time. As you can see, both increase and reach a plateau. So watching this result together, we can say that the C3S surface reprecipitation in water as CSH is associated with both the increasing film thickness and adhesion. And this results in an evolution of the paste with time. Also, IFM confirm these findings, IFM atomic force microscopy. So with a tip, we are going to check the surface of a C3S without water in air, and you can see that the thickness here is 0, the roughness is almost 0. And then if we add water after half an hour, we have a roughness of plus minus 10 nanometer. We did XPS on both SFA surfaces and IFM1, and we confirm that what we have is calcium silicate hydrate. Another example that is really interesting in the same line is the rehydration of alkali activated slag due to cache formation. While we have this A due to the aluminium that is contained on the slag. But before that, what is an alkali activated slag or an alkali activated binder in general? Is when we have byproduct or low calcium binder which need to be activated to make it more similar to OPC. In our case, we have a very good slag, the GGBS or ground and granulate blast furnace slag, which has typically this composition. So you can see calcium oxide, not as high as cement, but good, silicium oxide and aluminum oxide. So this aluminum is responsible to cache, as I will show you in a minute. So this GGBS need to be activated because it has not as much as calcium ion as OPC, and it cannot reach as high pH as in OPC. So we add alkaline activator, either solid or liquid. Solid are better for the environment, and they are also less harmful for the workers because we can do a dry mix and just add water as in OPC. So, as I said, when we mix all together with water, we have an alkali activated slag paste, which is formed like in OPC by dissolving and reprecipitating some hydration phases called cache, which is a CSH with aluminum oxide in the middle. So it's a very similar process, but in that case, we are considering a low calcium ions binder, which is a bit slower than OPC and allow us to have more time to predict to measure and predict the physicochemical behavior. So what we did is make an alkali activated paste with this quantity of GGBS and activators. We fix a water to solid ratio, which can be both used by in situ XRPD and SAUS. So in situ XRPD are classical XRPD, but the novelty is that we can put this fresh paste and spread between two plastic foils. and then do in situ XRPD measurement in transmission during more or less, we choose 5 hours, but you can continue as much as you want. We choose 5 hours because we want to match it with the testing in oscillatory rheology. And the limitation of our instrument is 1 hour, 1 hour and a half. To overcome this limitation, we prepare more sample at the very beginning, and then we test, for example, the first fresh, and then the other one, we let it age in closed tube to avoid any evaporation, and then we remix externally before being loaded into the rheometer. In this way, our windows is longer. Here you have the result. Let's start with in situ XRPD. Probably you are familiar with the XRPD spectrum, so a lot of peaks which correspond to the crystalline phases of your material. In our case, the nanocache at the very beginning is not so crystalline because we have nanocrystalline disk, but how they stack is not so ordered. So we can see something on the low angle intensity. There is a bump that increases with time. And this is how we trace the long angle intensity as a function of time. You see that there is an increase. I also show you the derivative as a function of time to let you see that after 1 hour, the cache formation speed up until reaching a maximum and then go down again. In rheology, we have our time structuration of these several samples which are externally aged and remixed before charging on the rheometer. And we can see that we have the G prime as a function of time. And the first hour show a very little reactivity. Then we speed up after 1 hour, we reach our maximum after 2 hours, and we go down. So the trend is really similar to the derivative. So we can conclude that the cache formation is associated with the buildup of cohesion of the AS paste. And in general, that South is able to detect macroscopically the early reactivity of cementitious pastes, as is confirmed by in situ measurements that there are more complex to handle and also more difficult to have in a lab. So now the second part, can we describe the physicochemistry of cementitious pastes? And in that case, I will show you South measurement of an OPC and the same alkali activated that I showed you before. So these two systems, as I already told you, has a different calcium content. And for this, we want to do some amplitude sweep test to define the LV, and in particular to track the linear storage modulus and the critical strain that we can also call cohesiveness and deformability as a function of volume concentration. So each point you will see will be a different singular test, which is repeated 3 or 4 times, that give you an idea how the deformability and cohesiveness evolve with the volume concentration. We want to do that to probe the interaction at the nanometer scale at rest. So not staying in the solid-like regime. Here you can see the linear storage modulus and the critical strain as a function of phi or as a function of the water to binder ratio for an ordinary Portland cement. We use a parallel with the model proposed by Shi and co-workers, and we see the trend of these two values as a function of phi. And when G prime increase with phi and also the critical strain, we can say that we have a strong interaction in the paste. If we see the alkali activated slag in the same water to binder ratio range, we see that the strong interactions start from a certain volume concentration. Both, in fact, here increase, while below we have that for an increase in the linear storage modulus correspond a decrease in the critical strain. And this is mostly due to the amount of calcium ions that we have in the pore solution. On one side for OPC we have 20 millimolar circa, and on the other side, on alkali activity slag, we have circa 1 millimolar. So the thought we had is like, okay, let's try to increase the calcium ions in the pore solution by adding 20 millimolar of calcium chloride. In this way, we can increase the calcium ions without affecting the pH and also all the other equilibrium with the other ions. As you can see, the new black points show a strong interaction all over. It means that now the pore solution is more similar, and it acts also, the paste has a more similar behavior. In order to check if what we measure with our amplitude sweep is correct, we add PCE, so polycarboxyl ether. PCE is a classic super plasticizer for OPC, is optimized for OPC, is fantastic. One drop allows you to have a very high workability. In the case of alkyl activated slag, we have no effect because we don't have enough calcium ions on which the PCE can absorb. So what we do? We do some mini-cone slump. We take a mini-cone, we fill it up, and then we put it up to see how the spread looks, and we measure the spread. As you can see, for alkyl activated slag, the spread is really similar to the initial diameter of the cone. It means that it has a low workability, and this is one of the problems in using alkyl activated slag. If you add PCE, we have no effect. If you add PCE and calcium chloride, you can see that the spread increases. It seems small, but it really changed the workability. So it has not the same effect as in OPC, but show that the key parameter is calcium, and we can detect it with SAUS. So to conclude this second part, SAUS is able to macroscopically probe the physicochemical status of fresh cementitious material. So really the interaction at the nanoscale. And now the last question. How this measurement I show you in the last slides can help develop new sustainable materials. To show you that, I will couple SAUS with X-ray powder diffraction mechanical testing, and I will show you an example on clay and one on recycled high-performance concrete. Starting from this one, our RHPC is a 2-year-old citrate-free OPC, which was grinded and milled to obtain a powder, which has a very small D50 of 35 micrometer. And in order to see if this powder has a residual reactivity, we use XRPD in a classic way with the powder and an internal standard. And here you can see the reactive phases of OPC, which was used for make this HPC, and our recycled HPC, so after 2 years. Obviously, the C2S, C3S, C4IF are less after 2 years of hydration, but this residual reactivity is really promising. So we decided to do some SAUS, in particular time structuration. And so we have our storage modules as a function of time for 2 different pastes, OPC at water to binder ratio 0.4 and recycle HPC at water to binder ratio 0.3. These water to binder ratio were chosen to have a similar initial G prime. And as you can see, as in XRPD, we have a residual reactivity. We don't reach the evolution of OPC, obviously, but again, is really promising. So we decide to do HPC concrete to verify is the compressive strength as a function of the replacement of recycled HPC as a binder, not as an aggregate, really as the fine fraction. Here you have R0, which means 100% OPC, and here you have R100, that means 100% recycled HPC. We measure the compressive strength after 1 day in green, after 7 days in yellow, and after 20 days in violet. So you expect that the compressive strength decrease with the increase of recycled HPC as a binder substitute. Now, this is normal. But what we didn't expect also was this residual reactivity of R100, so when only RHPC is used as a binder. In fact, we can reach 22 megapascal after 28 days, which is not bad at all. So we can say that the residual reactivity of fresh recycled HPC pastes is confirmed by the concrete after 28 days. Another example I want to show you is the milling activation of clay. So, as I showed you before in the schematic, raw clay alone is not reactive. So, one way to convince clay to be reactive is milling. And what we wanted to do is take raw clay, milled several times and sieved to have the same particle size distribution, and then make some fresh pastes at water to binder 0.8. We do the time structuration, so storage modulus as a function of time. And then you see that for raw clay, we have no evolution at all. And then the evolution increased after 15, 30, 60 minutes. And then at 120, we come back with the G prime at the same value at the raw clay. This is because we have a degradation of the powder, because we keep this powder in a very small milling machine, which get heat up, so it arrives at 55 degrees. So we have really a degradation, so we decided to stop at 60 minutes. Then we made some compacted clay mortar at a lower water to binder to avoid shrinkage, as you can see here in the picture. And we measure the compressive strength as a function of the milling time at equilibrium moisture content. And as you can see, we have the same trend. So raw clay after 30 minutes and after 60 minutes, rheology and mechanical properties match. So we can say that SAWS can be a very good predictive tool for early selection of promising sustainable cementitious materials that is really helpful together with complementary techniques when we need to study the physicochemistry and interactions of sustainable and locally sourced cementitious pastes. So the take-home messages are the same question I tried to show you in this talk. So I hope I convince you that SAWS can decipher the build-up of cohesion in cementitious system and describe the physicochemistry of these pastes, and also the more important, that help develop new sustainable materials. The long-term vision is continue to characterize the physicochemical behavior of sustainable cementitious systems with more and more complementary techniques and materials. And the other point that I would really like to do is connect quantitatively, because what I show you is more a qualitative connection, SAWS measurements on paste, so the first hour of life of this paste, with the solid mechanical properties, so after days. And to do that, we will need artificial intelligence and modeling, and I hope in future collaboration. After that, I would like to thank all the collaborators that allow this work to be so multidisciplinary and interesting. Here you have the extended references for your personal information. And then last but not least, I would like to thank the research unit of building material for support me every day, and you for your listening and attention. Thank you very much.